Brad slides.
Lambdas in fourth.
Lambda.
Yes, we can.
All right.
All right, I feel like we've accomplished
Have
something.
everybody mute.
Okay. All right, let's give this a go.
If you're not Brad, mute now.
Okay. So I'm gonna talk about doing lambdas in fourth. Lambda expressions are a sort of a practical variant on the lambda calculus. The idea is that you want to be able to represent a function in the abstract. So you want to be able to sort of capture all the things about a function and sort of pickle them up. And ideally, it's also something that closes on its environment so that you capture sort of all of the things that were present at the moment that the lambda was created. The lambda calculus was invented by Alonzo Church in 1930. It is on its own a complete model of computation. It consists of just the idea of variable substitution by way of a lambda, and then the application of a function. The language Lisp sort of turned this into the inspiration for a programming language where this the syntax is made more explicit. And so here is sort of the abstract function that takes in a single input and squares that input. And this concept has gradually found its way into the majority of contemporary programming languages. So Python got it, I think, fairly early in its history. It was later added to Java and relatively recently added to C++. Rust had it, I think, from the get-go. So could we have this kind of a functionality for Forth? Well, Forth is has the excellent property that it is very much what you make of it, and it's a very expandable language. So let's explore what it would take. Ideally, I'll mention that well, these examples all square a number. You want to do something a little bit more than those examples show off. You want to capture your environment. And originally in languages like Lisp, they used something called a dynamic environment. But now typically what the expectation is when you have a closure is that you would like it to lexically close. And that means that you want it to capture the symbols that are around it at the point that it's created. And it's actually kind of a nice property to actually make lambdas and closures useful. So in Lisp, something like this, it lets you create an adder where you pass in a value n, and then you create as the return value of that operation, the function which then adds n to a number. And so what would this look like in Forth? Well, the idea that I had, at least for this exercise, was to expand the behavior of locals and then to add a syntax for starting a closure. But this has a bunch of different memory management implications that we'll look at here briefly. So this is the syntax that I landed on, and we'll talk about how I was able to make this something implementable. But the idea would be, suppose you wanted to have a word which returns the execution token for squaring a number. I introduced these bracket colon words to surround creation of a closure, and then the content inside is the body of the closure. And then in this particular case, all the meat of it is happening inside. So this is just returning the squaring operation. And then because the word execute assumes a conventional execution token, I've decided to separate out and use a separate word to invoke closure. So I call it invoke. And sort of continuing on, what we want to do is also have this close on the surrounding environment. And in this case, if you've got sort of nested layers of these closures, you want to make sure that you capture from the outside. And so this is the same operation that we saw before done in Lisp. done in fourth, where you would have the value n come in, and then the idea is that you return a closure that takes n and adds it to a number. And so it's applied here, by first you create this adder and put it in X, and then you can invoke it on 4, and you can invoke it repeatedly because it's been pickled up. So how are we going to implement this? Well, locals are going to be important, but while they're standardized, there are a lot of implementation specific details about how to actually make them work. A fairly typical implementation strategy is to stick them on the return stack. This is what I do in micro eForth. There are other possible approaches, but this is sort of the common one. But it immediately sort of raises an issue, which is if you want to be able to do something like this, where n is still remembered at the point that the word adder returns, you've got a problem, because locals, their scopes go away on word return because they need to, you need to drain the return stack. And so sort of a fundamental consequence is that if you want to be able to support closures, you're going to need to have locals be somewhere other than the return stack. So where can we put them? Well, they may need to live a long time after return, and they also have the property that they may in turn contain the address of other closures. And so we're going to have the other problem of memory management, when to free them. So let's look at what other languages do. Well, in Lisp and Python and Java, a garbage collector is used, and then languages like C++ and Rust will stick them sort of sometimes in the stack or the heap, and then they're basically use careful lifetimes around scopes to be able to decide when to free that piece of memory. And the challenge, I think, for fourth is that none of these two is a terribly great fit, and there's a few reasons. Let's look at garbage collection first. Well, there's sort of the idea with garbage collection, recall, is that you want to free data only when you can sort of demonstrate that it can't be reached. And there's sort of three broad types, and it's really two, and then sort of permutations. You either have your data in memory, and you eventually end up copying it somewhere else, or you have you have it somewhere fixed in memory, and you try to figure out when you can collect it while leaving it where it is. And there are advantages and disadvantages to each of these. They have sort of there's a lot of complexity that can go into performant garbage collectors, but typically performant ones will actually be a hybrid combining sort of both of these. The thing about these, so let's circle back to this question of how to do this in fourth. Well, if we did something like careful lifetimes, the problem is that I think, at least as far as I've been able to reason out, it requires compile time type information. And there are folks that have tried to introduce sort of stronger typing to fourth, but I think it's not trivial to do, and it sort of doesn't slot in as nicely. A garbage collector requires runtime types normally, but there is a type of garbage collector called a conservative collector that doesn't require as much typing information, although it does have the slightly negative property that there are cases where it can live leak. So I'm going to go with the third one just because that's the easiest to slot in. I think there might be some clever thinkers who might be able to proceed down these other two roads, but this is where I went. So a conservative garbage collector, it was an idea it came up with by a guy named Hans Bohm in 1988. It's the idea that you treat any value in memory that looks like it might be a pointer to a garbage collected object as if it is. So you sort of conservatively assume that if something could be a reference to something, you assume it would be. It's a type of strategy that only works if you're your garbage collector is a stationary collector, because if you move things around, you have the risk that a pointer in memory might not point to the right place anymore. And while you can
Brad,
conserve, yes.
um, you're dropping out a little bit once in a while, so
Oh,
could you make sure to stay a little closer to the microphone and keep
let
your
me lean
volume?
into the microphone. Sorry about that.
Yeah, no problem. Thank you. Great talk, by the way. Thank you so much.
So the issue is that if, while you can be conservative about assuming that a pointer to a GC'd object or could be a real reference to it, you can't be conservative in relocating that pointer to point somewhere else, because it might just be a piece of memory that contains an integer that happens to look like the relevant thing. So you innately, with a conservative collector, need to use a stationary style collector. But it does have the cool property that you can do garbage collection in a language like C, and by sort of inference also in Forth. So how am I going to build my garbage collector? Well, I'm going to provide a simple interface to it where I'll take a pair of values, and I won't assume anything about those values. They could be arbitrary cells, they could be references to things. And then I can create a pair out of them that becomes a single value. And then later, if I want to unpair those values, I can get back out what I put into it. I'll provide a way to poke the collector explicitly for testing, although you shouldn't need to call it explicitly. And then I'll also provide a way to check to see if something looks like it might be a reference into memory. So how are we going to deal with locals? So instead of allocating a stack offset, which is typically what you would do for locals allocation, I'm going to allocate an ID and create an environment that will consist of a chain of pairs that are pairs of IDs and then the values that they contain. It's not a particularly efficient representation, but it at least is sort of straightforward to get right. And so what I do is I have a global that I hold the current environment for whichever word is currently executing. This obviously isn't thread safe. There are ways to make it so, but and then initially when a new value comes into scope, I'll initialize it with this word init local that will extend the environment to include this word. And then later, when I want to reference it, I can reference it by ID, and that allows creating the code once with a fixed ID, even though there could be multiple invocations of it. And so then there's just this loop to walk up the linked list of the environment to find the appropriate pair, or return a 0 if you don't find anything. So then all I have to do is implement bracket colon. And here the idea is that I need to save the current scope, that environment, and then jump over whatever code is about to come. And then actually I've got those reversed. And then I need to exit and then land from the jump. And then I need to, after I've done all of that, bind the piece of code with that I've just compiled, and then hook that to an environment. And so what this looks like for something like this adder word is that you build up a pair that contains a single element for n and its ID, and then that gets paired with an execution token, and then the one value that references that is what you can actually pass around as the closure. So I'm going to do a demo in a moment, but I'll just mention that obviously a thing that you might immediately find you want with this is the ability to store into locals. And just as locals allow you to use two, you can extend the scheme to introduce a way to write to memory. There are some wrinkles around making recurse work correctly, because you need to make sure that you're handling the environment appropriately in those cases. And so ultimately what this will allow you to do is to take something like this piece of Lisp code that does factorial, and you could translate it into something like this in Forth, where In this case, I'm doing the sort of roundabout thing of creating a local that will contain my closure, initializing it to 0, and then creating a closure that does factorial and storing it into that value. And because fact is referenced recursively, the whole thing can operate. You can also, this is borrowing from the Structured Interpretation of Computer Programs book, but here's another iterative implementation of factorial, and you can do sort of the same kind of a pattern in Forth. You can, of course, use all the usual tricks with closures to build. You can build up pairs again from scratch out of closures, which is kind of cool. And I've gone through the exercise of converting another one of the, if you're familiar with the, there's the structured, the SICP book has a bunch of interesting Lisp examples that you can now kind of readily convert and use in Forth to do things like implement rational numbers in a fairly small number of lines of code. So at this point, I'm going to pop out to a demo. If I can manage to deal with my screen being partially blocked. All right, so I'm going to go to here, and I'll just briefly take a look at what the code looks like. So I've got a heap of 1,000 nodes, very arbitrarily, and then basically what I do is for the Bohem collector, I need to have some words to recognize when a word is actually inside of the heap, and so there's some careful calculations here to do that. I have to implement a mark and sweep collector, so I've got a bunch of separate values for the marks. I'm inefficiently using a single byte. And then I have code to implement mark. And then I also have code to implement marking a range of values and then recursively reaching in. And then the sweep operation gathers everything up into a free list. And that lets me implement my collector, which provides a pair, and I will do a garbage. Whenever a pair is requested, I need to do a collect. I'll collect it. Oh, actually, I skipped over an important part. In this mark word, I go ahead and I mark I blank out all of the marks in the mark data structure, and then I use everything on the data stack, everything on the return stack, and everything from this heap not, which is all of the words that have been defined since I created the garbage collector, and use any of that data as a potential root. And so then I can build up pairs and unpairs by just pulling apart cells. And I also implement set car and set cooter. These are Lispisms to be stored at each of the two cells. And then, so that gives me a garbage collector. And then I can build lambdas by keeping track of the current identifier. And then I have some words for manipulating an environment, clearing it and the identifiers. And then here's my code for initializing a word within the environment, a value within the environment, getting a value, setting a value, and then what I can ultimately do, a lot of this is actually just cribbed from my locals implementation. And then ultimately, when it comes time to create a local, I simply parse it out and add it to the environment, the scope create word. And then bracket colon builds a scope and then closes it. And let me now go ahead and actually run. I've got some samples that have the things in the slides here, but actually one of the most interesting things to look at is take this like a word like factorial. Let's actually see what it looks like when we look at its code in terms of how it gets compiled. And so what ends up happening is that that n variable, gets assigned an ID of 1001, and it gets turned into initialization of a local. And then apologies, that's actually the N word, and then the 1002 is the fact exclamation variable, and then the ahead and then surround the closure so that we're jumping over the closure, and then inside of the closure, 1003 is used for X, and it's initialized, and then we retrieve its value, and then we compare it to 0, and then do our recursive invocation of ourself. And then after this ahead then, we're then able to bind to this address, which is just the address of the code right after this ahead. And so we're keeping it in a form that the decompiler is able to understand while still being able to build a closure here. And then we can put in factorial 5 and we get out 120. How am I doing on time? Okay.
Beats the heck out of me.
Okay, excellent.
You're fine.
Cool. So I'll show one more. So this is I've got that word make rat. This is to make a rational number, and that obviously doesn't make a lot of direct sense, but we can do some cool things, like we could make a rational number of this will be 1 over 2, and we can take another one, 1 over 6. Or sorry, 6 over 8, and then we can add these two, and that'll just give us this arbitrary token on the stack. But if we do print rat, we can print it out and get 5/4. So, and I'll at this point take questions.
Recursion. That's your example.
The question in case they didn't hear it.
The question was recursion. Is recursion possible? And so, for example, factorial here was in fact doing recursion, because inside of this closure, it's invoking the contents of ID 1002, which was itself the closure. So it's calling back through itself.
So how does it work? So the 1001 is ID within environment.
Yes.
So recursive will create multiple environments.
Right? Let's see. So each time it is, and so unfortunately it is not able to do its proper tail call, if that's what you're getting at.
Yes.
It is not correctly doing tail call.
Okay.
And that is a wrinkle that I have not yet figured my way around. And it's a bit of a puzzle there. I've thought about having alternate ways to explicitly do a tail call. And actually, if I pop out here to in a non oops, is that visible? That's covered with the thing here. I will temporarily move it down. You can explicitly do a tail call, at least in micro eForth, this way. But that actually doesn't help you with these environments, because the environments unfortunately need to get sort of reset back to their entry state.
Right.
I think the thing that would be necessary in order to make it possible to have it properly do a tail call is I would have to have some hooks into the beginning of word entry, because what the issue is that I need to make sure that on entry to the word, I know when I'm done setting up the environment, so that's the point I jump back to rather than the very beginning.
So garbage collector need to be background task, basically, right? So how do you run it?
So the collector is so it is unfortunately not a parallel collector, and so what it does is inside of the this pair creation word, collect is invoked when you run out. So you have every time you exceed. So it's not running. The collect isn't running every time, but if the if the free list is full, then it forces
You
it.
can put a timer, say, if
Yeah.
how many times you could run it.
Yes, you could force it. You could force it more often if you wanted to.
You can maybe adjust it.
Yeah, and there's a deep black art to getting garbage collectors good and proper. But
So have you looked at the reference counting mechanism? So
yeah, that's another good possibility here. I think for handling sort of full generality though with lambdas, I don't know that you can.
I don't know.
Yeah. I think it will work for many of the cases, but if you have any kind of sort of self-reference, it's where you're going to run into the same issues. Yeah.
I think Objective-C combines lambdas with reference counting. Does anyone know? That's correct.
It has automatic reference counting. Yeah. I'm pretty sure that's true.
Yeah. I believe Objective-C will tend to use schemes like arena allocation and things like that, where you're able to sort of just clear the slate periodically. So
Okay, why don't you unscreen share?
Let me
So we've reached the point in the meeting where we're going to do a photo op and bathroom break. Part of this is that Brad will put up a picture of all of the attendees and screenshot it, and that will be posted on the website. So if you do not want to be part of this screenshot or multiple page screenshot, turn your video off now, or switch to a suitable but not obscene picture thereof. Why don't we, Dave, why don't we stand against the back white wall here? What do you think about that?
Fine.
Okay.
So I'm going to separately screenshot that.
Screenshot
All right.
as in any way that you can to get the
Okay.
best picture of everybody that's there on the
Okay.
screen.
So if you're, now's the time to be on camera,
If you don't want your
folks.
picture on the
I'm
website,
gonna
don't
grab a
stand
few
against the wall.
shots.
If you're grim, frown.
1,
Not
2,
smile.
3. Say cheese. 1, 2, 3. Cheese.
But we'll see what happens. Right?
All right. I'm gonna go to page 2. 1, 2.
Sorry.
This may be helpful if later you want to.
All right. I think I've got the folks in the Zoom.
Surprise.
We're gonna momentarily go back here for the photo.
I'll sit here like a Civil War hero.
That was Sam, I think.
Have all your limbs.
No ne'er-do-well.
Put it on the table.
So is that merch from your Star Trek?
Well, maybe I'll put it on the table and move it.
No, actually, I had
Well, that's kinda what I was
received
thinking.
it as a birthday present along with a trip to the film
shorter
location where
legs.
they filmed the corn scene.
Oh, you're coming down already.
It's not Red Rocks, it's someplace else in California that reminds me of it, but
Cool.
I'll send you the information. Yeah.
There's a guy named Bill Will who does commentary. He's a YouTube video personality. I don't know what the right word is these days. But he has a life-size drawing standing behind him. Or at least he did last time I looked. Oh.
One of our neighbors was a costume designer, had a full size original front entrance way of his house.
Oh man, that'd be scary on
Yeah,
Halloween.
I never took a photo of it. That's exciting. First time I walked by, it was when it's there. That's cool.
Yeah, I'll just crop the bottom off. So what we're gonna do is, I gotta, hold on. I gotta set this to.
Actually,
Hello, can you hear me?
I can hear you.
We can
Um,
hear you
I'd
here.
like to make a
That's
presentation.
Stanford.
Oh, sure.
What's that?
I'd like to make an impromptu presentation regarding the last topic, like lambdas and fort. I've got an implementation that's like far simpler, and
Is
I'd
this like
like to share
5
that.
minutes, or is this like December?
5 minutes or 10 minutes top. Like I can talk about a very like okay. I'm just gonna start if that's cool. So this is
We're taking a photo here.
We're going to be conducting
Oh.
the meeting according to the agenda to the extent possible. After this
Okay.
break, we'll proceed with the agenda, and then we'll try to squeeze you in at the end. Is that all right?
Sure. Yes. That'd be all right. It's just like since lambdas are anyway. Sure, of course.
We'll try to squeeze you in before lunch or
I'm intrigued by what you propose, but nonetheless.
before green erase. If not, we'll beg you to come back in December and elucidate.
Sure. Like when is that? When would that be? How much time? Okay. Anyway, I'll be on the meeting anyway. So okay, cool.
Yeah, this is the one meeting of the year where we try not to let the agenda descend into chaos to the
Okay,
extent
so,
possible.
it's on a 10-second.
Yeah, let's get back to the meeting. Okay, hit the go button
So
like the
hopefully
fuse.
this will work.
Okay.
Dun 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 dun. 8, 7, 6, 5, 4, 3, 2, 1.5, 1.
Okay, we'll do one more.
One more.
And then afterwards, we're gonna do a roll call, so. when I-
Okay, so press the go button, do it again.
Yeah.
We'll get to
It's
that
not-
while it's counting down from 10. So anybody who hasn't done this before, you'll say your name and then go back to your seat.
Excellent. Okay, so, I'm gonna start the video, and after you say your name and record that, you can move out of the line. And I think I'll start at the bottom first. Okay, let's go.
Miles Williams.
Samuel Feldman.
Respect to lambdas, I'm gonna have I have strap frames. And actually, I make the comparison with lambdas. Also, the memory management. I follow Arthur Whitney's.
And
You'll see reference counting. Also, and one of the things. Anyway, already.
Almost as if it was programmed.
Simple idea. That's exactly. I don't like the line.
Okay, we're going to restart the meeting, guys, so close the door if you still want to talk. I allege Falvo's going to speak. So what's your deal? Do you have slides?
What's that?
You have slides?
Strictly speaking, no, but, how did you want to do this?
I don't.
You can either.
I wanna go home and take a
if it's easier, you could either join the Zoom room or you can
Sit up here.
sit up here, and if you can get your slides onto my device, but either or, whichever is the easiest for you.
I have network access.
And
So yeah, so let me join in on the Zoom real quick. I should probably move up there anyway, just because of the microphone.
Is that how us live people are doing it? We are.
You can either join the Zoom or use this computer.
probably easier
But
to
I'm
join
not
the
plugging
Zoom.
into an HDMI.
You can if you want.
Thank you. It won't do anything though.
Yeah, it'll put your slides up on that.
That monitor, but not
So
into
we'll-
the Zoom.
We'll unplug the Zoom from
But
that
nobody else-
monitor
but
and
nobody
plug you
else-
in.
But nobody else will see it.
Yes.
Well, if you're not on the Zoom, you could do, what I'm saying is you would do both. You
Sure.
would put
I
your
wasn't
slides
prepared for that,
directly
so I
on the
think I
screen
have to get
for no
some-
discernible reason and
All right.
join the Zoom so that all the Zoomers
I
could
did know
see.
that having Zoom was a prerequisite to present. so I have to go for it.
I'm sorry about that.
Okay.
It's a new process for us.
I was expecting the traditional plug in the cable and go.
So
Yes.
we have to disconnect this for him, or?
No, he'll just join the.
Oh.
You will need to mute, Sam.
I'm gonna mute.
Actually, technically, he could use his microphone if he'd rather. So
Okay,
yeah, we mute this.
I'm
one.
gonna mute this one. You use yours.